Conditions for the uniqueness of a line. Welcome, everyone. Let's begin our discussion on the conditions for the uniqueness of a line. Now, think back to your previous studies in two-dimensional geometry. You'll remember that if I give you a single point on a line and tell you exactly what its slope is, you can draw one, and only one, specific line. It's a very straightforward way to define a path. However, as we move our focus from a flat plane into three-dimensional space, things get a bit more complex. In 3D, the simple concept of slope is no longer enough to pin a line down. This is because, in a 3D environment, a line can tilt or lean in many different directions across the X, Y, and Z axes. A single number just can't capture all that movement. So the big question is, how do we uniquely define a line in 3D space? To ensure there is one, and only one, line that satisfies our requirements, we need to provide more specific geometric information. In the next few slides, we are going to explore the two primary conditions that allow us to lock a line into a single, unique position in space. Condition 1, a given point and a parallel direction. Now that we've established that a single slope isn't enough to define a line in three-dimensional space, let's look at our first specific condition for making a line unique. The first way we can uniquely determine a line is if we are given a specific point that the line passes through, along with a given direction that the line is parallel to. Now, remember what we discussed in the previous slide. In 3D, we can't just use a single number for slope. Instead, in 3D geometry, we represent this direction using something called a vector. To help you visualize this, let's break the concept down into three parts. First, think about the point. You can think of this point as your anchor. It provides the starting position of the line in space. We can call this point A, and we represent its position using the vector A arrow. Second, we have the direction. Because, as I mentioned, a single number can't describe a 3D slope, we use a second vector, let's call it B arrow, to indicate the direction. Any line that is parallel to this B arrow will move in the exact same orientation. Finally, look at the result. If you are standing at your anchor point, point A, and you are forced to move exactly in the direction of vector B arrow, there is only one possible straight path you can take. There's no room for deviation, which is why the line is unique. To make this even clearer, let's step away from the math for a moment and use a real-world example, a laser beam. Imagine you are holding a laser pointer at a fixed position in a room. Step 1, the exact location where you are holding the laser device represents our given point. Step 2, the way you aim the laser, the specific angle it makes with the floor and the walls, represents our given direction or our vector. And step 3, once you have fixed that position and set that aim, the beam of light creates a single, unique straight line across the room. This is a perfect setup for our next condition, where we'll see what happens if we don't have a direction vector, but instead, we have two different points. Condition 2, two distinct given points. The second way a line is uniquely determined is simply by passing through two distinct points in space. Let's break this down conceptually. Suppose we have two different points, which we will call point A and point B to describe their locations in our three-dimensional coordinate system. We use their position vectors, which we'll denote as a vector for point A and B vector for point B. Now, why does this work? It goes back to the most fundamental rules of geometry. There is exactly one, and only one, straight line that can connect any two separate points. But here is the most important part for your calculations. If you have these 2 points, you can actually derive the direction we talked about in the previous slide. By calculating the vector from A to B, which is found by subtracting a vector from B vector, you've essentially created a direction vector. This means that having 2 points is mathematically equivalent to having a point and a direction, effectively turning our second condition back into our first condition. To make this more concrete, think about a real-world example. A tightrope walker crossing between two skyscrapers. First, imagine the anchor point attached to the first building. That is our point A. Second, imagine the anchor point on the second building. That is our point B. Once the rope is pulled taut and made perfectly straight, It forms a single, unique line. There is no other straight path the rope could possibly take to connect those two specific anchors. Now that we have explored how a point and a direction can define a line, let's move on to our second condition. In the next slide, we will look at some common pitfalls to avoid when applying these two conditions. Common mistakes to avoid. First, please be careful not to assume that a single point is enough to define a line. In the 2D geometry we studied previously, we used slope, but in 3 and D, a single point is simply not sufficient. If I give you just one point in space, imagine a starburst pattern where infinitely many lines are radiating out from that one center point. To lock that line into place and make it unique, you must have that extra piece of information we discussed earlier, either a specific direction or a second point. Second, a very frequent mistake is confusing a point with a direction. You might find yourself mixing up the position vector of a point, which we call a vector A, with the direction vector, which we call vector B. To keep this straight in your mind, try to remember this distinction. The position vector tells you exactly where the line is located in space, acting as your anchor, while the direction vector tells you where the line is going. One is your starting position, and the other is your heading. Finally, when we talk about our second condition, using 2 points, never ignore the requirement that the points must be distinct. This means they cannot be the same location. If point A and point B are actually the same point, you have effectively lost your second piece of information and are back to having only 1 point. As we saw, 1 point alone cannot create a unique line. Now that we have covered the 2 primary ways to define a line, I want to pause and discuss some common pitfalls. Even if you understand the concepts of points and vectors, it is very easy to make certain logical errors when solving 3D geometry problems. Keep these distinctions in mind as we move into our final summary of the key takeaways. Key takeaways. First, remember the fundamental principle. A line in 3-dimensional space is only uniquely determined when it is fixed in both position and orientation. This means we can't just know where the line is, we also have to know which way it is pointing. To recap our 2 specific conditions, Condition 1 states that a line is unique if we are provided with a specific point that the line passes through, along with a vector that the line is parallel to. Think back to our laser pointer example, the position of the device and the direction of the beam. Condition 2 tells us that a line is also uniquely determined if we are given 2 distinct points that the line passes through. As we discussed with the tightrope example, once those 2 anchor points are set, the path of the rope is fixed. Finally, it is crucial to remember the mathematical link between these 2 conditions. If you are given 2 points, let's call them point A and point B, with their respective position vectors, and B, you can actually derive the direction yourself. By calculating the vector B minus A, you find the vector that connects the 2 points, which serves perfectly as the direction vector for that line. All right, we have reached the end of our lesson, so let's bring everything together with our key takeaways to ensure you have a solid grasp of this topic. As long as you keep these principles in mind and avoid the common pitfalls we discussed earlier, you will be well equipped to handle any problems involving lines in 3D space. Great job today!